Good afternoon, everyone. Welcome all to another session of our DPS Journal Club. Today with us, Mr. Dipanjan Chakraborty. He finished his master from Calcutta University and joined here as a PhD scholar in 2015. He is he's working under supervision of Dr. Rumite, and he also is our also previous coordinator of our journal club. So today he will tell us about his works like flocking and hunting in groups. So, Dipanjita, you can start now.
Thank you. Thank you, Saptarshi and Team Gluon for inviting me to this. Okay, I am audible.
Yes, yes,
Is the
yes.
connection is clear? Okay, thank
It
you.
is clear, Dipanjan. It's
Okay,
nice.
okay, thank you.
Go.
So, thank you, Saptarshi and Team Gluon for inviting me to the Journal Club talk. And so, basically, uh, as Saptarshi said, actually, I will not talk about my work specifically. So, basically, I will talk about some important models which has already been developed previously, and those are based on basically flocking and this cooperative hunting, this hunting in groups. So the overview of my talk is that, so first I'll go through some examples of this collective motion in a living system, though in non-living system also the collective motion has been studied, and it has of utmost importance. So then I'll go about what is flocking of birds and what is basically collective motion in living matter, and how importantly how the birds fly together. And I'll mainly focus on this in the first part of my talk, a Vicsek model. So this is a particle based model to explain the general underlying principles of flocking and other collective patterns. And in the last part of my talk, I'll talk about this group chase and escape. So basically, a group of when a group of predator chases a group of prey, so how that could be modeled in lattice and also in off lattice model. So the first model, this Kamimura's model, is on lattice, in a square lattice, is a simple model, and this the second one is this Luca Angelini's model, which was published in PRL in 2012. So, and in the last section I will just explain my one of my work where just I'll give you the overview. So the collective motion has been studied firstly in different living systems and also now in non-living systems also. So here you can see the different patterns of feces. So here in the first picture you could see the feces are moving around and with random directions, if you talk about the correlation, there is no correlation among the velocities. So in the second picture you could see they are moving in an ordered fashion and moving in a particular direction. So basically this is the school of fish, and here they are the feces are forming a ring kind of structure. And in the fourth example, here they are clustered into a aggregate. So these are the various fascinating patterns which living matters generally show. And in the next slide I'll go in a video, so where it will describe the flocking motion. I think so I should mute the, okay, this mute button is not here. Okay, so basically the flocking pattern and how the starling flocks generate different patterns in the sky, maintaining a coordinated motion, and also the distance between them is fixed, or that varies actually when they are turned. So in the next few slides I'll talk about how to model this kind of flocks using this Vicsek model. And this is the first model where it was generalized in off lattice model. Sorry for the audio. I have to mute the audio. So
You don't have to. The audio does not is not transmitted.
okay, then it's okay. So even without the bird flocking, In other kinds of living system, we could also observe the collective motions, like in lane formation by ants, or in swarming of insects, or even in the human crowds. If we look at the bird flocking, so the first model was proposed by this C.W. Reynolds in 1987, and the basic assumption, so basically he was trying to model a graphics, basically, and computer graphics. And the basic assumption he was taken is that first is the collision avoidance. So when the birds are flying in the sky, they will not collide with each other. So there must be some avoidance, or the collision avoidance interaction between them. And even when they are moving and coordinating with each other, because they're forming a self-organized and coordinated pattern, so the velocity matching should be there. That means every bird tries to match the velocities with its neighboring birds. And third, the attraction among the groups. So there should be some attraction up to a certain distance. So otherwise, the pattern after a certain time, it will not be there. The pattern will diminish. So basically, so the basic assumptions that he was taken was also taken by this Vixek and his collaborators, and they proposed a model of this is also of lattice model, and which was published and this is widely used in today's research work, this Vixek model. So in the Vixek
So
model,
Dipanjan, one
yeah,
question.
yeah.
Yeah, so is the wind, drag, etc. taken into account here? I mean, there is some kind of a effect due to the winds as well. So I don't know. I mean, if it's a windy day, corresponding to a less sort of
Okay, so
more
you are
fluffy
telling
day or
this
something.
the
Yeah,
effect of wind or the drag forces. No,
yeah, drag
here
forces exactly. Viscous drag and all, are they considered, or that is because
so
that
for the
probably
simple model they have not considered, but after that, but you could consider. Actually, these are solved in the overdamped limit.
over damp. Yeah, yeah. So that is
Yeah,
also there, is it?
yeah. So viscous drag is
Okay.
there. Uh, so basically the forces. So here. Okay, I'll come to that later.
No, it's
So
okay. I
noise force
mean,
is
that's
there.
part of your
Uh,
talk. Later on, you can come to it when it comes. You don't need to
yeah.
answer immediately. I was just asking you.
Hmm, hmm, hmm.
Okay. If it's there late, then they'll
And
show it
repulsion
later.
is there. No, actually, in this simple model, I think the dissipation it's not there.
There's no
That
there.
is
But
that
they
that
are generally considered in these swarm, I mean, bird flock model and all, is it? It should be there.
yeah. In a in a
Okay.
in the swarm case, it should be there. But if you solve the equation of motion, then you can take it and also can solve as a ordinary differential equation. You could write the Langemark kind
Because
of
I feel that generally, due to
Hmm.
the motion of a neighboring bird, that also will change a bit of the drag, no? I mean, that probably also should affect a bit. I mean, that is like it's like, we do this hydrodynamic interaction in fluids. So that is
Exactly.
essentially the liquid,
So
mediating some
actually,
kind of
actually the
viscosity. Here, does it?
interactions are there,
Yeah.
and so the drags. So if you look at this neighboring interaction, and that's why it will change the direction. So
Ha ha.
basically,
Okay.
if you are saying that if it changes the direction, that actually
Affects the neighboring
encompasses
bird.
the other things, other
Yes,
forces
yes,
actually.
yes, yes.
It
So
could
that
be,
is
but,
more probably in a
but
more
not
complex model.
directly the frictional force is not included here,
Okay, but not in this, but in
because
other
they
other
are
models
actually
they are.
systems. And so if we go into the model, you will understand, because we are taking the
Okay,
velocity
sure,
to be
sure.
constant
Okay.
always. So
Acha, acha.
so
This
just
model they don't consider.
yeah, yeah.
Okay.
So in the Vixek model, so initially the active particles are placed in a random 2D space. So basically this should be a square. So I have so take it as a square, and in this space the active particles are randomly spaced, and the absolute velocity of all the particles are taken as same. So that's why I was telling that since these are the active particles, so it could generate its own force. So basically, the dissipation is not taken into account. Basically, Otherwise, if in a physical system, the velocity will decrease or increase depending upon the interactions. So here the velocity of all particles is taken same, uh, assuming that it is generating its own energy, and each particle assumes so the basic building part is that, uh, so if you take this particle, it will consider a radius around it, so just like this. So if you take this particle, so it will take a radius around this, and it will calculate its neighbors. So these blue are the its neighbors. So those who are in this interaction radius, so these are its neighbors, and calculate the average direction. So this red arrow denotes the average direction of the neighbors. So the neighbor of this one. Okay, where is the mark? Yeah, this one. So in the next time step, it will move along this average direction with a random perturbation. So the random perturbation is added as you can make an analogy as with the temperature. So basically, if we go into the equation, how the positions and the velocities are updating. So basically, the at the t+1, the position of this prey, the position of the particle, it will be constructed as in previous position plus the new updatation that will depend on the average velocity. So the average direction of the velocity should be calculated as this theta average is the average direction plus a fluctuation in the direction would be given. So this is a delta theta, and this delta theta is represents the noise, which is a random number which is chosen from a uniform probability distribution. And how to calculate this delta theta, sorry, the theta average? So that is basically the tan inverse of this average of sine. So this is the component along the y direction, and this is the component along the x directions, and these are all averages over the radiuses, because we are talking about the neighbors, right? So for each particle we'll update that according to its neighbor. So the average direction has been calculated plus some perturbation is added along the direction, and that's how the position of the each particle will update. So using this rule, if we calculate, okay, another thing is that we use this periodic boundary condition here. So basically taking as the system as an infinite system. So initially, if we put these particles in L cross L box with, so if we change the, so first we take the L is equal to 7. So here the density of the particles will depend upon this L value, and this N is basically the strength of the noise term. So initially, at initial time, you will see that the particles are randomly distributed along every direction. So there is no correlation among them. So if we change the density and noise, so in the lower noise and lower, so basically if you change the L, so density is proportional to the 1 by L squared. So basically this will be lower. So for the lower density and for lower noise, you could see the small cluster formation by these particles. And as we, so this is for the higher noise and at a density L equal to 7. So for this is the initial time t equal to 1. If we go at a longer time for this case with the, so this could be taken as the higher density case with respect to this, right? Because L is changing. L is 25 here, L is 7 here. Okay, so for higher noise, you could see there is there is no correlation. So the correlations are very minimal, and velocities are basically they are random. Some correlation should be there that we have to calculate, but as the time goes on, because this first part at initial time and at the second t equal to 200, there is no such correlation among the velocities. But the interesting fact is that as we increase the density, so if we decrease the L more, the density will increase and the noise strength will be noise strength we have taken as lower. So here you could observe that the particles are moving in an ordered fashion, and they are almost almost moving in a particular direction. So the interesting fact is that we have uh, got a transition as we vary the density and the noise. So we have also observed the cluster, small cluster formation, ordered fashion, and also the randomly moving particles. So if we now uh, calculate the order parameter, which is defined as the average normalized velocity. So this is the average normalized velocity. So if all the particles are in the moving in the same direction, then the total velocity will be n into v. So then the average velocity will be 1, right? So if the velocities are random, then the sum would be 0 basically. So there is a, so if we fix the densities, so in this plot the densities are fixed and we vary the noise strength, and here we will see a kinetic transition from higher density to the lower density. So sorry, here will transition from a higher order parameter average velocity to a lower or average velocity, because as we increase the noise, the velocities will average velocity will be nearly zero, because in the higher noise you could see the snapshot where there is no correlation among the velocities. So here n are changing, but l are accordingly changing, so that keeping the density as constant. So here we fix the noise and vary the density. And here also we observe a transition from 0 to 1. So this transition, kinetic transition, it will look like a similar order parameter transition in equilibrium system. So the system we are talking about, these are far from equilibrium but non-equilibrium systems. So here we could also observe they have actually also calculated this uh, critical exponent beta and delta in the thermodynamic limit. Basically they have calculated for different bigger system sizes, and then plotted this average velocity as a function of this eta c rho minus eta c critical, and calculated this beta and delta values. So this model actually is very helpful, particularly in biological system, because in the physical systems mostly they will follow the uh, mostly they are not active. They could not generate its own force, right? So basically these most of these biological systems are active systems, and you could easily uh, employ this model on different kind of uh, biological experiments, and also in theory. So this is the one kind of model where you could get a flock in higher density and a lower noise. And other interesting aspect is that here in a recent study, this Ballerini et al. So they have analyzed the trajectories of flocks of a few thousands of starlings, and they have shown that if each bird interacts with a fixed number of neighbors, so basically they have reported the experimental thing where they have shown that each bird interacts with a fixed number of neighbors. So this on an average 6 to 7 neighbors. So in the previous model, Vicsek model, so they have used a metric distance r, and within the r they have calculated the neighbors, right? Here if we use this fixed number of neighbors, or these are also told also named as this topologically interacting particles. So basically if there are 6 neighbors, so they are interacting with this even if they are residing out of the radius. So they basically sense the nearest ones and then go into the go on interacting, right? So these kind of interactions have also been studied, though I will not go into the detail. But recently our group, ma'am and Vijay, has done the work on topologically interacting birds or topology interactive particles. So the ordered motion actually comes faster or comes efficient if the particles interact topologically. So this paper will come shortly after few days. Sure. So in the next part of my talk, I'll go into the collective motion of predator and prey. So actually, previously various studies have done where one-to-one chase and escape has been studied. So basically, one prey is moving and the one predator tries to catch it. So these are all studied extensively, and also the multiple predators when they attack the single prey. These have also been done earlier in this two paper. However, in the natural scenario, if, we could see that the multiple predator is uh, attacking the multiple multiple targets or multiple prey. And also there shows that that different cooperation level, the different cooperation among the predators that would help the uh, predator group actually for efficient catching. So the Kamimura and Ohira, so they first proposed a simple model uh, of chase and escape on a square lattice. So I'll describe this model, and also uh, analogous to this model, Luca Anginelli proposed another model which is off lattice model like the fixed model. So I'll discuss these two models in the next few slides. So how to model this group chase and capture in lattices. So the chasers and targets. So basically, the chasers and targets are initially randomly placed in a square lattice. So they take a square lattice and randomly place the chasers and targets in the on the edges. And so basically, if a chaser is there and target is there, so they first calculate the distance, right? So they first calculate the distance, and suppose say there is another here. So the nearest one will be chased, right? So they first calculate the distance, and at each time step they try to decrease the distance. So chaser always tries to decrease the distance by one lattice spacing. And what the target will do, the target will always try to escape away. So that's why it will try to increase the distance increase the distance by 1 unit, by one lattice spacing. So here, if you look at the probability, so basically the chaser could chase the target, so they have to go in this direction to minimize the distance, decrease the distance. So either chaser will go in this direction or in this direction. However, the target has also two options. It will not go here, because then the distance would not increase. So in this case the distance would increase in these two cases. So and also if they lie in the same axis like this one here, the chaser has only one option. It would go to the nearest to the target, and target has three options. So it will go here, here, and here. Okay, so with equal probability, right? So using this, so basically we are implementing the stochasticity also in this model. And okay, and another thing is if two or more chasers are present. So suppose two chasers are from equal distance. So let us take another chaser here. So what would happen then? So basically, then it will choose the target will choose the chaser uh, mm, with equal probability and move away from it. So using this one and all the steps, so the steps I have told, all the steps will go simultaneously. So simultaneous update will be there. And So what they have reported is that they have calculated some statistical quantities such as the total time of the target, total time of catching of the final target, sorry, total time of the uh, total catch time, or the total catch time could be also incorporated as the time of the lifetime of the final target, right? So here for a particular here we keep the number of target constant and vary the number of chasers. So as we vary the number of chaser, we could see that the time for entire catch, these are the probability distributions of of the lifetime of the final target. So as the number of chaser increases, this time is also increasing, right? Number of chaser, sorry, as the number of chaser decreases, the time is increasing, right? So for if there are 10 chasers and 10 targets, so the will time will be higher in case of lower chaser. For 500, you could see that this peak is at the lower time. And these are the probabilities. Okay, so in the next case, so another significant case is that when the number of chaser and number of targets are same, so the distribution deviates from the normal distribution. So here here this for these two cases, these distributions are normal or Gaussian. However, in this case, it deviates from the normal distribution because the effect of group chase and escape has been included here. Okay, so now uh, another thing, tau is calculated. So we have already told the capital T. The capital T is the total catch time. That means we have started from a configuration and how much time is needed to catch all the targets. And tau is the average lifetime of all the targets. Okay, so for the first to catch the first one, T1 is needed. So like that, T1, T2 plus Tn, and then averaging it. So tau denotes the average lifetime of all the targets. So if we calculate that, the total catch time and the average lifetime of all the targets as a function of number of chaser. So as we vary the number of chaser, so we will get two power law regimes. So here at the lower chaser concentration, we will get this total catch time varies as a function of so basically this is something constant into nc to the power minus 3. So the power is 3 here, exponent, and there is a crossover when the number of chaser is 5 times of the number of target. So at this, hello,
Yeah, please continue.
okay, so when the number of chaser is 5 times of the number of targets, then the crossover happens. So here the power law regime, here the power is basically 3 to the power 3 by 4 basically, so 0.75. So the rate of so basically as we increase the number of chaser, the time will obviously decrease, but the rate of decrease has two power law regime, and this has this and if we plot the other thing, that means if we keep the number of chaser constant and then vary the number of target, then the total catch time monotonically increases, because in the system, if we increase the number of targets and keep the chaser constant, so then it will take more the chasers will take more time to catch the targets. So this rate curve will increase monotonically, whereas the average lifetime also increases, but after a certain after up to a certain value of the number of targets, it will then again decrease. So that is basically because of the cluster formation. Because if you use a huge number of targets, because in the we are here they are reporting from 100 reporting the results for 100 cross 100 lattice. So the that means the 10,000 can be occupied. Uh, so here the number of targets are very high. So the cluster, so here the small clusters are formed of targets, and also if they are in the they are confronted by the chasers, uh, small cluster of chasers, then they will catch instantly. So that effect, for that effect, it will it is decreased after a certain peak actually. So the main interesting fact is that if we solve this chase and escape on a lattice, we will get two power law regimes, and we are getting a crossover when the number of chaser is 5 times of the number of targets. So they have also calculated the cost factor. So so what is the, so if we ask the question, so what is the right number of chasers for a given number of target? So right number of chasers means, so the exact number of chasers you need to kill all the targets in an efficient way. So that basically depends on these factors. So basically they have generated this unit cost. So C is the unit cost per target. So we are dividing it by the per target because we are keeping the number of target constant. So C is the unit cost for the group of chasers to finish the job per target. So if we give an example, so just look at this. So this will depend on the number of chaser and the total catch time, right? So if we look at the cost as a function of number of chaser, just look at the rate curve, because other things I have not explained here. So the rate curve, so at the extreme right, so if the number of chaser is 9,990 and other number of target is 10, so the total capacity is 100 in 100 cross 100 lattice is 10,000. So among which 9,990 has been captured by this has been captured by these chasers, and the 10 positions has been captured by the targets. So here what would be the dynamics? In the next time step, all the targets will be killed. So at t equal to 1, all will be killed, right? So here if we calculate this cost function, that will be nc is this into total catch time is 1, because in the next time step all will be captured. So nc into t divided by nt. So basically 9,990 into 10 divided by this 10, it will give you 1,000. So it will give you 1,000. So here the value is 1,000. And also if you look at the cost function as a function sorry, as if you look at the cost per target as a function of chasers, here you could see a minimum. So these are this minimum number of chasers are required, and these minimum number of chasers are basically efficient to capture all the targets. And if you increase more, that is basically not helping too much. So there is a maximum cooperation, right? Okay, so the thing actually I have omitted here. So what would be the case if only one chaser and one target is there? Then there will be no capture, because in the model I have uh, here they have assumed that the velocities of the target and the chasers are same. However, in a model of Uama and Sato, so they have explored with fast chasers. However, the results are not too different. However, the power law changes in the low chaser concentration. So in the Sato's work, they basically the same work on lattice, basically with some fast chasers. So some fast chasers are introduced. Then the scaling is changed. Basically, in the low chaser concentration, the scaling is changed. However, in the high chaser concentration, there is no change of scaling. So basically, this 1.5 is the exponent in the low chaser concentration. However, the higher, it will not change. In the searching ability has also also could be modeled here. So in the coming models model, they have just introduced the searching ability, introducing the smart chaser. However, here they have basically assumed that uh, the search range of this each chaser and target is infinite. Mm, so you could also incorporate this search range of each prey and each predator, or each target, or each escaper. Sorry, each target and each chaser. So, so this model is basically the lattice model, though it's not too realistic, as the particles move in an open space, and uh, the Vixen-like models, or the agent-based models, or SPP models, self-propelled organism particle models, are more efficient in modeling this kind of realistic group chase and capture. So the Luca Angelini has done that in using this fixed kind of model. So basically, they also used two groups of SPP. Uh, one is prey group, one is the predator group, right? One is, or you can say, one is chaser group, if you can correlate with the previous one. One is chaser group and one is the target group. Okay, so the chasers are NC and the number of targets are NT. And each individual, according to the Vixen rule, they will move at a constant speed and velocities. And however, there would be a fluctuation, right? So the updating will be this. Updation will be like this, and the velocity will update using this kind of update rule, where this velocity unit vector can be described as a sum of these terms. So this term is actually, so since you know VICSEC now, uh, basically the velocities are they are calculating the uh, something is hello.
Yeah, you are audible. Just there are little bit noise.
Yeah, yeah.
Maybe everybody else should just mute their mic.
Someone is opening. Someone has opened his mic. His or her mic. Hello. Is it audible now?
Yes, yes, yes.
So, so this velocity unit vector is the sum of these terms. So the first term is actually the velocity alignment term that I have already described for this Vixen model, where they have taken a radius, and within the radius, how the organisms follow this average direction. Okay, average direction, and with a perturbation. So this Rn basically uh, rotates uh, along a direction. So basically, this is basically Vixen model with alignment interaction, and this term is the repulsive term. So basically, there are two groups, right? One is the chaser group, and one is the escaper group. So each chaser will not collide with another chaser, and each escaper will not collide with another escaper. So right, so that's why this steric repulsive force is introduced, which will consider that the particles will not overlap. Okay, and the third term is this. Uh, Basically, this is the attraction or the repulsion along the chaser, or the along the escaper or the chaser. So basically, each chaser will tries to uh, uh, attract towards the target, right? So here also a sighting range has been introduced, where the sighting range is RS. So in every species, uh, so in every organism, that means in chaser and in target, they will feel this force, this attraction force for the chaser, and the repulsive force for the escaper, because escaper will always tries to go away from the chaser, right? So that's why there is a force which is, and also this force has been modeled as they are getting the force from the nearest chaser. So if it is a target, it will get a force from the nearest chaser, and if it's a escaper or a target, it will, হ্যাঁ, and the vice versa thing. Okay, so this force RIKI, so this is a linear force basically P into this RI minus RK. Now the chasers will attract, so that's why if P is -1, then this equation is for the chasers and P is +1 for the targets. Okay, so now if we look at the dynamics, actually I was not able to include the video, maybe due to the format. So if we change now, if I change uh, the number of chaser as and calculate the total catch time, so here T is also the total catch time, right? So the total catch time as a function of number of chasers. So here is basically the ratio number of chasers by number of target. So as we increase the number of chaser, is it not audible? Hello?
Yes, it is audible. Please continue.
It's fine.
If
It's
we
fine. Just continue.
Okay, if we increase the number of chaser, then the total catch time shows again two power law regimes. However, the exponents are different here. Okay, and also these different colors are for different noise strengths, and also here they have calculated the how the number of target as a function of time, the number of target will decrease because the capturing is occurring, right? Because they are so as the noise increases, actually the capture time decreases. So these are the another aspect. The most interesting aspect is this: if we change the number of chaser or change the chaser concentration, then here also we are getting the the two power law regimes. However, the powers are different. So basically the general result is that, so in the group chase and escape, the general result is that two power law regimes are present. However, they are model dependent. That's why the exponents are different. So basically the dynamics is general. However, if we solve it in square lattice or in off lattice model, so these are basically same. However, the quantities are different. So these are the main significant result of this group chase and escape. Okay, and so I have not included summary actually. Okay, uh, so my work is also so in the past two works that I have talked about is of the cooperative interaction within the predator group, right? Here in my first work, PhD work, where I have showed the cooperative interaction within the prey swarm. So if we start from an initial configuration where the preys are taken as particles, just like the VIXEP model, they have taken they taken as particles, or VIXEP model or the leucoangiolins model, they have taken the targets as particles, and a nearby predator is chasing the group, and if this in this prey swarm they are interacting within a certain interaction radius, and if we change the radius, then we will see that a intermediate range of interaction radius is actually helpful for the prey survival. And if we use higher interaction radius or all are interacting, that is not helpful, and even a lower threshold is also there. That means minimum number of interacting prey should exist to make a coordinated motion. So for further reading, you could read my uh, this scientific report paper, which is published in the previous year. So that's all. If you have any questions, you can. So this is our group. This is my guide, Romi ma'am. This is Orkayon, Partho, Devangana. So they all work in this biological aspects, theoretical biology basically. So if you are interested, you can go to them. Thank you. If you have any questions, you can ask. Maybe I was not able to clearly specify things. Hello.
Yeah. So, yeah. thank you, Dipanjan, for such a wonderful talk. So
It
now
was a very
time for
nice seminar,
questions.
Dipanjan.
Yeah, so
Yeah,
Okay.
sorry. Continue. Continue.
yeah, so questions.
No one has questions. That means something is wrong.
No, no, not that.
I had a question. Hello, am I audible?
Hello. Yeah, yeah. I can hear you.
Yeah. So what happens when a predator catches a prey? The prey number decreases. That's fine. Does the predator number also decrease,
No,
or
how?
does
No, no, no,
the
no.
predator goes
So
on to catch some
the
other prey?
lattice model, or you are telling for the this this chaser model, the group chaser
Yeah,
escape?
yeah, yeah. The
No,
chaser
the
model.
chasers are present. No, chasers are not omitted. Chasers are present.
Okay. And
That's
one
why.
more thing.
That's why.
So
So the main result that shows that if you vary the chaser concentration, right? So basically, if, when you have 10 praise or 100 praise or 500, that will change. The total catch time changes. The average lifetime of the targets that will change. So when basically they catch the praise are omitted from the system, but praise are removed basically from the simulator system, but the chasers are present. Even in the particle based model where I have talked about this Vixek like model, here also the chasers are present. Okay, I can show the video actually where it would be more clear. Okay, I am presenting the full screen, right? Saptarshi?
Yes, yes. No,
So I
now
can
just the
now.
PowerPoint screen. Now it is only the
yeah,
PowerPoint.
yeah, yeah. Your entire screen is visible. Yes. Carry on.
So can you see this video?
Yeah, yeah.
So this is for the Luca Angelis model. So this is for periodic boundary, and so you can see the chasers are present, right? So they are chasing and killing the red are the red ones are the preys, right?
So which one is a chaser? The arrow one is a chaser. I couldn't
No, no,
understand.
no. These are chasing, right? So the black ones are the chasers.
Okay, black ones are the chasers.
Hmm. Yeah.
So we also see that
Hmm.
the chaser also forming a cluster there before
Yeah.
before
Caesar can form cluster there. Yeah, yeah. Hmm. And also the KZ configuration. So otherwise, okay, for the this model, for the lattice model, uh, if one predator and one prey is there, uh, there will be no capture, right? So
yes, yes.
predator has to cage down the prey to capture it. So even in this case also, you could see the video again where this kind of, so this is coming from this, so this the KZ configuration, it can't move. So yeah, not yeah, this small clustering has been formed. Yeah, this cluster is formed. So that's because they are interacting within a radius, right?
Yes. So
And they are also moving towards the praise within a radius.
so that means
This sighting
the
radius is important, right? Sighting
so
radius is important for all prey and predator.
so is that mean that before chasing the flocking is happening?
Before chasing,
Like all the
no, no, but the interaction. So in this case, actually the velocities. Uh, so the here the interaction terms. So if you don't use this force, so these two forces basically, if you omit this force, that is the catching force, right? That
Yes,
means
yes,
chaser
yeah,
tries to catch or the target tries to escape. This is the term, right? Other things basically the Vixek model. So it will flock, yeah, for the low. If you use the low noise, so this Rn basically is the noise, and this is interacting within a cell propulsion and an element effect within a radius. So basically the Vixek model, right? Within the, if you
yes, yes,
omit this term, so basically chase and escape you are omitting, then you will get the flocking, the first model that I have discussed.
yeah.
Vixek one, yeah.
So I have another question. Like
Hmm.
you show that below some noise strength, the cluster is happening in case of locking.
Okay, okay. This is first
Yeah, yeah,
model by
yeah.
Vixek. Okay, I am
Yes,
going into this. Yeah, yeah. Actually, actually here I have shown for different densities, right? So first you look at this for L7. So the density is proportional to 1 by L square. As you increase the density, sorry, decrease the density. L25 means you are decreasing the density, and also decreasing the noise, not only the density, also the noise, then you are getting the small cluster. And if you look at the time evolution, okay, so first focus on this thing. So here the density is constant, and this is the initial time where all are randomly directed, right? And in the second case for T2000 as 200, you could see that nearly same kind of structure is there, just small correlation you could get. It's more random, it's nearly the minimal, the correlation is minimal, right? So what is the question actually?
so like my question is
Huh.
how temperature affect the flocking? Uh, as it,
Temperature with noise, yeah. So if you change the noise, so yeah, that is the curve that I have explained. So here I have calculated the average velocity, right? The average velocity of the group. So if you calculate the average velocity of this group, what would be the value? So just assume that all are in a particular direction. So what will be the average velocity? Normalized average velocity. So it will be one, right?
yeah, yes, yes.
It will be one because all are directed in a. So it will be one. So as the noise is minimal, so noise is zero or very less. So then the average velocity is one, nearly one. So basically we are getting the ordered structure. And as we vary the noise, keeping the density constant, because changing the density will change the number of neighbors within the radius, right?
Yes, yes.
So the model is actually you are calculating the average direction within the circle or within the interaction radius actually. So if you change the density, so here the change density is constant, but changing the noise actually, that's why you are getting the transition, right? So this order parameter, this is a second order kind of transition. So that is you can compare it like this ferromagnetic sorry paramagnetic to ferromagnetic transition below the Curie temperature.
Yes, 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 yes,
It's kind of that transition, yeah.
yeah, right, understood.
Mhm.
Any other questions?
There's one small question, Dipanjan.
Hello, hello sir.
Yeah, hello, can you hear me?
Yeah, yeah.
Yeah, okay. So, in this model, your chasers are eternally hungry. So, to say, after capturing one target, they immediately go for the next target, right? There is no gap in the.
Yeah,
They want
yeah,
to.
not so, yeah, there is no gap actually, yeah, there is no
Okay,
gap.
so just confirming that.
Okay, so this is not actually the natural kind of thing,
Yeah, but I
but
don't think that will change your result much, even if you introduce a gap. Yeah.
that will not change, I think, yeah. Mhm. The delta t, if you introduce some time gap, I don't think the result will change, because we have then we have to run for longer time to get the result, but the total catch time, the scaling will remain same, I think.
Yeah, that's what my understanding.
Mhm. Mhm. The scaling will remain same.
Yeah. Thank you,
Dipanjan,
Dipanjan.
I mean, is there any kind of generally match with any experimentally found observable or something with these
Like
with respect to
that this lattice model is not actually the empirical studies have not been done to capture these things, but this cooperative predation has been already I think these exponents have not been matched experimentally, but this collective predation, that means a group of predators that they actually cooperate among themselves to catch a less stronger prey. So that have been studied in the
So
literature.
what do they match?
So here they actually match the qualitative things. That means if the number of chasers increases, then how the uh, total time of catch decreases. That these qualitative things. So basically, actually, you have to do the reverse thing. You have to do the model and then have to check ecologically. Uh,
Mhm.
so if in my model, so this is my published. So if you change the interaction radius within the prey, we are getting it getting an optimal in the intermediate regime. The survival is maximum. So that thing is uh, that thing is reported in some of the cases where if if they interact
Some of the cases, money, what are they looking at animal?
that
What
means
is,
if you look at the marine predators, right? So
okay.
if they're forming clusters and a stronger predator attacks, then actually the forming the cohesive group is disadvantageous, right?
Okay. So then
So
spreading
here
out is
you
what makes
have,
sense.
so the
The
qualitative
density
matching
is
is
lower
there,
or something.
but empirical studies, that means if you are saying that you have to match the exact one, then you
But
have to
then you would probably
model
match
the
some
experiment,
dynamics, right?
model the experiment
Some,
along using this.
some dynamics you need to match, right? Okay, how fast the density changes and all that kind of stuff. That is probably what you can match with any real data. I mean, how quickly the
The patterns. So
physical
in my
distribution
paper,
changes from.
actually, I could say that there's the patterns are matching. So that
But
I
do you see any time evolution of the
yeah, time.
pattern? Or?
So for the my model, actually, I have all explained the. Okay, just give me 1 minute. I've all explained the other works, actually, the works done by other groups. So here detailed. So here the matching is that the patterns, actually they also match the patterns. So here you could see, is it visible?
Yeah, yeah.
Yeah. So this ring kind of,
But I mean, success would probably depend on how quickly you can change the initial pattern to a pattern that is going to be more formidable for the predator to actually be successful, right?
yeah.
Oh,
But
this is time, is it? Oh, this is time.
if you consider a system, and then you can apply some rule, and then check the patterns which are matched with natural outcomes, then it is
But that t equal to 1,000, what is the unit? Because
these
that
are
is like
basic
with
scale
seconds,
time,
then it's easy.
scale
That is,
time,
huh?
not
Sorry?
second simulation time scale, actually.
That is, yeah, some
Yeah.
kind of random
Uh,
unit, no?
so basically, the predators are confused.
This
So if they
cannot be
interact
second.
within interaction rate is zero point 0.5, then the predators get confused and it couldn't catch. Right. So as you increase the interaction radius more, so there is small subgroup formation. These all are patterns are reported in School of Fishes.
But they don't actually
Swarming,
put
sorry
units
for
to
the
that
second.
time.
That you could see the swarming kind
Do
of.
they actually put units to the time, or that is just kept as simulation time?
These I have done. So here it is a in the experiment they have not they actually they are the time in days, actually. So if you go in the
Days,
ecological studies, the time in days. So in the swarming you could get the time in
days, days.
minutes or hours, actually, not minutes.
But that cannot be right. I mean, you cannot have an hour-long prediction. I mean, typically it is
Yeah.
much faster.
Typically so if you see this coexistence of prey and predator, this kind of confusion effect, where this kind of confusion effect is there, they will
I mean,
uh,
because
they
you
will be confused
probably
after
that.
a certain time and go away, basically.
I mean, that
Or
time will
otherwise,
probably determine how fast the interaction is, or something like that, right? I mean, how quickly you would switch from an initial initial distribution to a final distribution. that would also be a measure of how successful you are from prevention of predation.
That means you are
Right?
telling the
And then,
efficiency of predation. That means
yeah, efficiency,
the
exactly.
NT that the efficiency also could be calculated. That people have
I mean,
calculated.
I'm saying that that would actually lower. I mean, that the time would completely affect how efficient the predation would be, and that is where you can really match with real data, where you are, take videos of the successful attacks. And
Yeah, yeah,
I
yeah.
don't know, are these actually done?
These successful attacks experimentally they people have done, but matching with the
Not,
exact
they've not,
data
they've
they have
not
not
seen.
done. Mm.
Maybe okay,
Most
it's
of the
not done.
studies have
Okay,
not done. Some models, some critical models are there. They
okay.
have done, but using simple model, it is tough
Yeah,
to
yeah, of course,
calculate that.
of course. Right, right.
Yeah, then
Okay,
you have
thanks.
to consider more interactions and other
Yeah,
things.
yeah, yeah, sure.
Yeah.
Okay,
Mm. Yeah.
good talk. Thank you.
Thank you.
So if there are no other questions, so I
Mm.
just request you all to unmute yourself and give Dipanjan the round of applause.
Well, here it is.
Thank you.
Thank you. Good talk, Dipanjan.
Okay. Thank you, sir. Yeah.
So goodbye everyone. We'll see you soon.
চাফা দিবি না?
Online starting, sorry, offline starting তখন দেখা যাবে।
ঠিক আছে, টাটা।
ওকে চলো। আচ্ছা তাহলে আমাকে একটা কথা বলো যে when there are মানে তার মানে শীতকালে একমাত্র ফ্লকিং বেশি দেখা যাবে rather than
না
গরমকালে।
না শীতকালে আরে আরে তুই তো ভুল বুঝলি রে। না না না, টেম্পারেচারটা তো অ্যাকচুয়ালি ডেল্টা থিটার কাজ করছে, মানে ডেল্টা থিটার যে ফ্লাকচুয়েশনটা আমি ওটাকে বললাম
মানে
যে
স্প্রেডিংটা।
মানে না ওই ডিরেকশনটাকে একটা নয়েজ দিচ্ছিস তুই বেসিক্যালি। না না, টেম্পারেচারের সঙ্গে কোনো ব্যাপার নেই। আমি অ্যানালগাস টু দ্য টেম্পারেচার বলেছি, তুই কি টেম্পারেচার ভাবলি? ওটা টেম্পারেচার না। মানে
আচ্ছা
তুই ডেল্টা থিটাটাকে চেঞ্জ করবি, মানে বেসিক্যালি একটা পাখি উঠছে ধর তোর, এবারে ও পাশাপাশি চারদিকে চার পাঁচটাকে দেখলো, দেখে একটা অ্যাভারেজ ডিরেকশন দেখলো, সেই দিকে যাওয়ার চেষ্টা করবে অ্যাকচুয়ালি, ঠিক আছে? এবার সেই দিকে এক্স্যাক্টলি না গিয়ে একটা ছোট্ট পার্টারবেশন নেবে, এবং সেটাই পার্টারবেশনটা আমি বলছি আর কি ফিজিক্যাল সিস্টেমে ওটা টেম্পারেচারের মতো, বুঝলি?
আচ্ছা বুঝতে পেরেছি।
মানে টেম্পারেচারের সঙ্গে কোনো সম্পর্ক নেই। না না না।
ওকে ওকে।
হুম হুম
ওটা সাম কাইন্ড অফ মানে র্যান্ডম থিংস আর হ্যাপেনিং ওই যে ওই ডেল্টা থিটার মধ্যে। যার একটা
এক্স্যাক্টলি,
এক্সাম্পল।
মানে একটা নয়েজ দিচ্ছিস তুই বেসিক্যালি সিস্টেমকে, একটা নয়েজ দিচ্ছিস, ঠিক আছে? এবার নয়েজটাকে তুই টেম্পারেচারের সাথে কল্পনা করতে পারিস, মানে ধর তুই যেটা প্যারাম্যাগনেটিক সিস্টেমে করিস আর কি, যে স্পিন গুলো এরকম আছে, তুই মানে এবার টেম্পারেচার যত কমাচ্ছিস তত ওদের মধ্যে নয়েজটা অ্যাকচুয়ালি কমছে, বুঝতে পারছিস?
হ্যাঁ হ্যাঁ হ্যাঁ।
তো নয়েজি সিস্টেমটা কমছে বলে ওরা যখনই ওই 20 টেম্পারেচারের নিচে যাচ্ছে তখনই একটা অর্ডার স্ট্রাকচার দিচ্ছে এবং একটা ফেরোম্যাগনেটিক ফেজ আমরা দেখতে পাচ্ছি। তো সেই রকম আর কি, এক্স্যাক্টলি সেরকমই ফ্লকিংটা হচ্ছে।
বুঝতে পেরেছি।
হুম,
থ্যাংক ইউ।
ঠিক আছে। হুম
উঠলাম দেখা হচ্ছে।
হুম হুম।